the one question that we just turned in that you said I did wrong. I don't know how to fix it.
Oh, the one that the part A part?
Yeah.
Okay. So
I tried very hard and I just could not.
I don't know either.
Yeah, Masana came and asked me about it.
I thought I was so clever, and then it was. I was like, oh, cool.
Do you know the counterexample you used?
Yeah.
I'm just trying to remember what the problem it was. What's that?
We used counterexample.
Oh, good.
For
20 part A, right? Yeah. Okay.
That's good. That's a good sign. It really is.
Oh, that one, right?
Yes.
Okay. So if we just rewrite some things, this first part, of course, means that n would divide the difference. And it would divide the product, right? Okay. Problem is that we don't know that n is prime. If n is prime, then I can say it divides one or the other, but it's not necessarily prime. So the way I would attack a counterexample is try to figure out something here where I can make those two pieces multiply together to give me 0 mod n, but then those individual pieces aren't 0. So what counterexample did you come up with?
I wasn't thinking about criteria. I just did 0 is congruent to 9 mod 9, and it's like 0 isn't congruent to 3 mod 9 or negative 3 mod 9.
That'll work. Yep, that works too. So 0 squared is congruent to 3 squared mod 9. But 0 is not congruent to 3 mod 9. And 0 is not congruent to 6 mod 9. Which is negative 3. 6 thing is negative 3. So that works. What kind of counterexample did you come up with?
It wasn't like a specific counterexample. We just kind of like basically said like if D divides, D could also possibly divide A plus B.
Gotcha.
So it's just the fact that they didn't specify that n was prime.
Correct. Yeah. If it's prime, it's true.
Okay.
Yeah. If it's prime, it's true. If it's not prime, then there's lots of counterexamples. You could do what? Oh, 2 squared is congruent to 6 squared mod 8, for example. No, that doesn't work. 2 squared is congruent to. No. Anyway, there's lots of examples. This works. I was trying to think of a different one off the top of my head. You could do. Could you do? Why is 6 and 2 not working for me? Because 2 and 6 are
the same with 16 or 25.
Yeah, you can do anything with the perfect squares. Yeah. Yeah, you can do the same kind of thing. Just use 0 and then do the thing that's half. When you square it, you get 0. And then, yeah, so anything that's a perfect square will work. Yeah, that works. Doesn't have to be a perfect square either. There's, like I said, there's lots of different ways that you can do it because there's lots of different ways to multiply things that are 0 that aren't 0 to start with. So, yeah, it's the fact that it doesn't have to be prime. That's the big thing. Yeah, because you can make your A plus B piece have a piece of n, and then the A minus B have the other piece of n that you need to multiply together to give you n. Yeah. Yep, that was it. Good. Okay. Other questions? Okay. I do want to do a couple of other results that are near the back of the book before we go on and do our discussion of general rings. This is actually chapter 13. We're not going to go through all of it. We're just going to do a couple of the results that lead into it. But the couple of results that lead into the big thing in chapter 13 is about talking about how you can do coding things. It's talking about public key cryptography. So Well, that's one of the reasons why I want to talk about a couple of the examples. We will use one of the results in here later on this semester, but it also helps with doing coding stuff, which keeps information secure on the internet. They do some smaller examples in here, but the idea, honestly, behind what keeps your stuff secure on the internet is that factoring is hard. So you take two exceptionally large prime numbers together, exceptionally large prime numbers, over 100 digits long, and multiply them together. So now you've got a composite number that has two prime factors, but try to break it back apart again, it's hard to do. Because what's your big technique for factoring numbers? Does 2 divide it? Does 3 divide it? Does 5 divide it? There's no efficient way to do that, unless, of course, quantum computers take over, and then we are kind of screwed as far as security goes. But
isn't that also how they generate credit card numbers?
Yeah, it's the same idea. Yeah, he does credit card number secure. Yeah. So anyway, I do want to talk about a couple of the results that are in this chapter. Like I said, we will use them later on this semester as well, and they're used for the coding thing. We're not going to spend time on the coding thing, but I do want you to know that there are, honest to goodness, applications of the weird stuff that we do in here. So there's a lot of things that mathematicians figure out and then, play around with. It doesn't seem like there's applications. And later on, somebody's like, oh, hey, we can use that for this. There's a whole field of mathematics called topology, which basically talks about things like a donut and a coffee cup are the same thing. They both have one hole. The coffee cup has a hole on the side with the handle, and the donut has one hole, so they both have one hole. So a lot of people call it rubber sheet geometry. What that means is that everything's flexible, but you can't rip it apart. So you can imagine that you could take the donut and take the hole over and then smash it in to make the coffee cup part, but you haven't really damaged anything. That's what topology does. It seems like you're just playing around with different things, but topology actually now is used in data analysis. There's a whole field called topological data analysis with the advent of being able to analyze large data. So it's amazing that people will discover things in mathematics. A lot of mathematics is done for mathematics' sake, but then later on, it's like, you know what, this thing might do this thing over here, and then it ends up being applied. So it's the same kind of thing here. The fact Euclid just worked with prime numbers back in 2,000 plus years ago, and now we use prime numbers to help us keep information secure on the internet. So anyway, there's neither here nor there. But I do want to mention that there are honest to goodness applications of stuff that we do in here. Some of the other stuff that we'll do later has applications to quantum physics, for example. Not that we'll do any of that. But anyway, so let's talk about the couple of results that I want to mention. So the first one talks about that if P doesn't divide C, and we have RC is congruent to SC mod P. Oops. I can write. Erase. Why are you not erasing? There it goes. Then R is actually congruent to S mod P. What does it look like we've done to both sides of that congruence? Or maybe equation's a better word there. What does it look like we've done? You got rid of the C, right? It looks like we've canceled off the C, divided the C out, whatever you want to call it. Notice the important part of that is that P doesn't divide it, right? We talked about last time things either being units or zero divisors, and units are the things we can divide by, right? And we said that something is a unit if it's relatively prime to what you're modding out by, which is exactly what we have here, right? If P doesn't divide C, then P and C are relatively prime. So then C is a unit mod P, and then I can just multiply both sides by its inverse. So that's why this particular result is true. But this pops up in the next theorem, or lemma. I actually called it lemma, but I want to call it a theorem because we're not doing the big theorem of the section. This theorem is actually referred to as Fermat's little theorem. It's just a wee little theorem. So you may be familiar with Fermat's last theorem. Fermat's last theorem was, Pythagorean theorem, x squared plus y squared equals z squared, has integer solutions to it, like 3, 4, 5 works, right? But if you change that exponent from a 2 to any other positive integer greater than 2, there are not any integer solutions to that equation. So x cubed plus y cubed equals, and what I mean by that is all of them are integers. So x cubed plus y cubed plus z cubed does not have any solutions in the integers where all three are integers. The x, y, and z are all integers. Or x to the fourth plus y to the fourth equals z to the fourth, or so on up the line. And that's Fermat's last theorem. When was that talked about? In the 1600s, I think, if I remember right. Anyway, the reason why it's attributed to Fermat as his last theorem was posed. He wrote in the margin of a book saying, I have a proof of this, but it won't fit in this margin. 400 years later, the theorem was finally proved using mathematics that wouldn't have been available to Fermat at the time. Used some elliptic curve theory stuff, if I remember correctly. I haven't read the proof. The proof is like 100 and some odd pages long, 160 some odd pages long. It's just huge. A mathematician named Andrew Wiles basically locked himself in an attic for 8 years working on it to prove it. Came out in 1993, 4-ish, if I remember right. So anyway, the moral of the story is people doubt very seriously that Fermat actually had a proof to the theorem just based on what was required to prove it. So in any event, this is a little theorem.
It's going to end up doing 5 lines.
Be amazing, wouldn't it? Anyway, so Fermat's little theorem says that if P is prime, oh yeah, I forgot P needed to be a prime in that previous result. I didn't put that in the hypothesis. I used P and assumed that I was talking about a prime. If P is prime and P does not divide, this time the book decides to use an A rather than a C. Then if you take A and raise it to the P minus 1 power, you get 1 mod P. To mention a little bit about, you mentioned a little bit about why we're going to use this particular result later on the semester. Before we look through at what the proof is, let's talk a little bit about what I mean by this. So we've already seen Z5, right? So if we raise, what this theorem says, that if we raise anything that's not congruent to 0 mod 5, so 1, 2, 3, or 4, and raise it to the 4th power, because that's 5 minus 1, we should get 1 mod P every time. Okay. Well, certainly 1 works, right? Because 1 to any power is 1. If you do 2 to the 4th, you get 16, which is certainly 1 mod 5. If we do 3 to the 4th, we get 81, which is also 1 mod 5. And 4 to the 4th is 256, which is also 1 mod 5. And it doesn't matter the prime. 0 obviously will give you 0 back out, right? But any other number between 1 and integer, between 1 and P minus 1, if you raise it to the P minus 1 power, you always get 1 every single time. Okay. All right. So what does this proof look like? Well, the reason why I wanted to do this, by the way, sorry. In particular, any Z mod P, notice that everything goes back to the 1, which is our multiplicative identity. So that means that we can always multiply a number by itself a certain number of times and get back to the identity. I might be able to do it faster, but I know for certain that I can do it within P minus 1 steps, right? And there are exactly P minus 1 numbers less than P that are relatively prime to P. So that's, like I said, this is going to be a concept that will come back later in the semester. That's why I care about the result. Okay. May not make a lot of sense why I care right now, but it will later, I promise. All right. So we need to figure out what a to the p minus 1 is. So we're going to create a product that'll give us a to the p minus 1. So the first thing we're going to do is we're going to consider a list of numbers where we've just taken the same a and multiplied them by 1, 2, 3, and so on up the line up to p minus 1. Is it possible for any two numbers in this list to be congruent to one another mod p? Let's think about that. So let's say you had, say, a p minus I and a p minus j were congruent. So we had a p minus I times a and a p minus j times a, and those are congruent mod p. That's fine. I can leave it like that. And the reason why I'm doing p minus I and p minus j is I'm kind of thinking about counting backwards, right? So my I could be 1, it could be 2, and it could be all the way up to p minus 1. Right? I'm just kind of thinking about it backwards, just the way that it's written there. What do we know about the relationship between P and A? Yeah, it doesn't divide, right? So what that previous theorem that we mentioned before, if P doesn't divide that coefficient, then what can we do with it? If it doesn't divide the A, what can we do with the A on both sides? Get rid of it, right? So this would say that P minus I is congruent to P minus J mod P, right? Yeah. And now, does that P matter? If you're modding out by P, does the P matter? No, I can just get that P is 0 mod P, right? So then I get negative I is congruent to negative J mod P. And now negative of a number, same thing as negative 1, but we know that 1 and negative 1 are units, so I might as well get rid of the negatives too, right? So I'll do that by this way. And make it I is congruent to J mod P. Remember now, our I only goes from 1 to P minus 1. If I and J are different and between 1 and P minus 1, can they be the same? Or can they be the same number? Can they be congruent to each other mod P? If they're between 1 and P minus 1, can they be congruent to the same thing? No, because they're all between 1 and P minus 1, right? We're not canceling anything out, right? So the only way this can happen, since I and J are between 1 and P minus 1, we must have I is equal to J. They can't be different, right?
Can you explain that again?
Yeah, sure. So we know that I and J are definitely between 1 and P minus 1. So when I divide them by P, the remainder is either whatever the I and the J are, right? There's nothing to cancel out. So the only way they could be congruent mod P is that they're equal. Okay. Yeah, that's what I'm saying. I did not explain it well the first time, so I'm happy to explain it again. All right. So they're not congruent to each other. That's the big idea. Okay. So I have, when we do this product, they are different from one another, right? That is a list of P minus 1 distinct things, right? We agree with that? All right. So what that means is we may have to rearrange, but one of these, and again, we're modding everything out by P, right? That means that one of these numbers and exactly one of the numbers in this list has to be 1. And then one of the congruent to 1. And one of the numbers in the list, and only one of the numbers in the list has to be congruent to 2, and so on up the line. Okay? So what we have here is this list of A, 2A, whoops, up to P minus 1 times A is what? Congruent. Well, I shouldn't say it that way. How do I want to write this? Well, I want to write it as each of these numbers, when I reduce it mod P, it certainly can't be 0, right? A is not divisible by P, and 1, 2, 3, and so on up the line is not divisible by P until we get to P, right? So this list of that is distinct. Well, is not the right letter. It doesn't matter. Is a why can I not erase? Now it decides to erase. Thanks. Is a list of P minus 1 distinct values between 1 and P minus 1. They're all distinct and they're all between 1 and P minus 1 mod P. Does that make sense what I'm trying to say? We know that they're not congruent to each other mod P, right? Distinct coefficients give you distinct remainders, right? And when we mod out by P, it has to be between 1 and P minus 1. It can't be 0 because P doesn't divide the coefficient and it doesn't divide the A, so it can't divide the product because it's prime. Okay, so I get a list of distinct values, and it has P minus 1 distinct values, all of which are between 1 and P minus 1. So that means that if I rearrange this list and do congruence mod P, I get the list 1, 2, 3, 4 up to P minus 1. Right? So what this tells me is that if I multiply those things together, we get that A times 2A times 3A times P minus 1 times A is congruent to 1 times 2 times 3 times P minus 1 mod P. The reason is that A is congruent to something in the list from 1 to P minus 1. 2A is congruent to something in the list from 1 to P minus 1 different from A. 3A is congruent to the something in the list different from A and 2A. And so on up the line, I have to exhaust it. There's a 1-to-1 correspondence between the list of numbers A, 2A, 3A up to P minus 1 times A and 1, 2, 3 up to P minus 1. Let me give it a specific example. Maybe it'll help illustrate. Okay. Let's let A be 3. And so my A is 3, my P is 5. Okay. So then I look at the numbers 3, 6, 9, 12. That's A, 2A, 3A, 4A. All right. Let's do mod P now. Mod 5. 3 mod 5 is 3. 6 mod 5 is 1. 9 mod 5 is 4. 12 mod 5 is 2. Now, so I've got this 1-to-1 correspondence between the things in my list and the numbers from 1 to P. That's what we're doing. And again, there's nothing special about the number that I picked or the prime that I picked, as long as it's not 0 mod P and we have a prime. So let's say your A was 2 and your P is 7. Let's just do another one, make sure that we're all on the same page with what's going on. The list then is 2, 4, 6, 8, 10, 12, right? That's A, 2A, 3A, up to 6A. All right? So mod 7 now, 2 is 2, 4 is 4, 6 is 6, right? 8 mod 7 is 1, 10 mod 7 is 3, 12 mod 7 is 5, and we've got that 1-to-1 correspondence again between the list of distinct values and our numbers between 1 and p minus 1 mod p. That's what we're saying. But notice that my list isn't in order, right? I don't have A is congruent to 1 and 2A is congruent to 2, right? They're mixed up, is what I was trying to say. But if we multiply them all together, we can rearrange them in order that we want, right? Does that make sense? Okay. All right. So let's go back up to our congruence here. We have how many A's in my product, in our product here? How many A's are there? Almost. Yeah, there's p minus 1 factors there, right? So there's p minus 1 A is there. So the left-hand side we can write as A times p minus 1. And just to simplify the notation a little bit, what are you left with if I pull all the A's out? I've got 1 times 2 times 3 times p minus 1. I want to simplify the notation a little bit. How would you simplify that notation if you do 1 times 2 times 3 up to p minus 1? Yeah, that's right. Go ahead. It's factorial. Yeah, it's p minus 1 factorial. Now, notice we have the same factor on both sides, don't we? We can cancel it off of both sides. We can get rid of it as long as we know that that factor is what? I can cancel it as long as I know the factor is what? Going back to the first result we talked about. Not divisible by p, right? As long as it's relatively prime, I can cancel it out. How do I know that that product is not divisible by p? How do I know that 1 times 2 times p minus 1 is not divisible by p? And you're right. It's because p is prime. What would p be trying to divide? What would p be trying? What would p be dividing here? Yeah, but in particular, what kind of a thing do we have arithmetically? What are you doing with all these numbers? Yeah. So you got p divides a. The other way. Quotient is dividing.
Shoot.
Well, there's the word product. P is dividing a product, right? You got a prime dividing a product, yeah.
Oh my gosh. Yeah.
If P divides a product, what does P have to divide? P divides A, B implies P divides A or P divides B. It divides one of the factors, right? Does P divide any of those factors? No. Okay, that's why this doesn't work. Okay. There we go. Woo. Yeah, if it were a 0, P would have to divide the number, which means P would have to divide the product, but P can't divide the product. All the factors are less than P. Right? Every factor of P minus 1 factorial is less than P, so P can't divide it. Right? So P does not divide P minus 1 factorial, so A to the P minus 1 is congruent to 1 mod P. Bless you. In fact, if you want to look up an interesting result on your own, there's something called Wilson's theorem, which talks about what P minus 1 factorial is congruent to mod P. I'll leave that for a discovery exercise for you. And by discovery exercise, I mean you can Google it. It'll tell you what the answer is. You can probably guess it just by doing some examples. Do 4 factorial mod P, do 4 factorial mod 5, do 6 factorial mod 7, 10 factorial mod 11. You can probably guess what the answer will be by the end. Anyway, that's neither here nor there. All right, so this is Fermat's little theorem. And again, the idea behind that is used in being able to do the public key cryptography, the RSA encryption. So if you look at the rest of chapter 13, that's what that's devoted to. Probably also in most discrete mathematics books. If you're interested in doing something with coding theory for an independent study in the future, I know Dr. Olson has done that with students before. You can talk to her about that. It might even be a good senior project, for example, since some of you will have to do senior projects. Well, the math ed students also have to do a senior project. Your senior project is called student teaching. It's not.
Really? We don't do senior project? No, dog.
No.
We still have to do honors capstone.
You have to do your honors capstone, but you don't have to do a senior project for math.
Student teaching.
That's what your senior project is. That's why we don't have you do the senior project.
That makes sense.
You're already doing the project. There's a lot of work involved in that, so you're already doing a senior project. That's why we don't make you do another one in math. I mean, you can if you want to. No, who wouldn't stop you? What's that?
Yeah, I said she
can
told
do
my free
mine if she
time.
All right. In any event, like I said, if you're interested in that at all, that it would be a good senior project avenue or a good independent study class avenue. So there's lots of work in there that you can do that's kind of fun. Yeah, if you like that kind of stuff. If you don't like that kind of stuff, then don't do it. All right. Let's go back then and talk about doing things in rings. So let's go back to chapter 3, which talks about what we mean by a ring. So section 3.1 just starts talking about definitions and examples of rings. To give you an idea of where the word ring comes from, when it talks about from an algebraic structure idea, most everything that you study in algebra comes from solving equations. The whole point of being able to do algebra is to solve something from an equation standpoint. That's where pretty much every idea in algebra comes from. So the idea where the word ring comes from actually comes from a certain type of equation. If you wanted to solve, try it this way. If you wanted to solve this particular equation, we have a polynomial equation that's equal to 0. It's what we refer to as a monic polynomial. Monic means it has a leading coefficient of 1, but rather than using all the words leading coefficient of 1, it's a lot of syllables. We say monic. We reduce the number of syllables to 2. So that falls into the Stickles law of conservation of syllables. Okay. So we have a monic polynomial. If we have a solution, if I know what a solution is for x, what that tells us is that I can write higher powers of that solution in terms of lower powers of the solution. I can write that specific element as lower powers, right? So in effect, the higher powers have ringed around to a lower power. That's where the word ring comes from, like a circle around. So the word ring comes from an algebraic idea. Again, like I said, most every algebra concept ties back to solving an equation or a system of equations at some point. Okay. So that's where the word even comes from, is an idea of solving an algebraic equation. Okay. So let's look at this particular type of equation and see what's going on. In this particular equation, how many operations do you see? 2. I see addition and I see multiplication. Okay? So a ring automatically has 2 operations that are defined on it. Okay? So a ring as a definition, a ring is a non-empty set of things we'll say R, because R is ring. So we'll use R for the denote a ring, with two binary operations defined on it, called addition and multiplication. Okay. Now, from what you remember from linear, just because we say the word addition doesn't mean the addition has to be a standard addition, and just because we say the word multiplication doesn't mean it has to be a standard multiplication, right? But we do have certain properties that the addition and the multiplication have to have. Right? So we talk about how they work with each other. So we've already talked about this sum, so I'm not going to belabor it again, but notice that if I want to be able to solve such an equation, I need to talk about being able to manipulate things around. Right? I need to be able to manipulate my addition. I need to be able to manipulate, hopefully I can manipulate my multiplication. But in general, when we try to solve equations, there's certain properties that we have to have, and then there's other properties that we like to have, but don't necessarily have. Okay. What I mean by that is, of course, if you have an equation like 3x equals 7, I'd like to be able to divide by 3. But it depends on what structure I'm in. If I want to say my solution has to be in the integers, I don't get a solution. Actually, this is kind of a cute story, which I'll tell you here in a second. If you want to solve the equation in the rationals, then you can divide by 3. Right? So it matters what structure you're in. So division would be nice property to have, but not necessarily. But if I want to solve the equation 3x plus 1 equals 7, I absolutely need to be able to subtract that 1 to the other side, right, for the addition part. So inverses we require for addition, but don't necessarily require for multiplication. So that now to my cute story. I had my nieces here yesterday afternoon to get ready for a little hoopsters in the afternoon. So they were in there, and they were doing math problems on the board. So my one niece really likes math, and so she's actually starting to do some. She's 8. She's 5'2", but she's 8. She's enormous. She is. She's just huge, and she won't stop growing. She just keeps getting bigger. But she's actually starting to do some algebraic thinking. So she's working with the multiplication. So she comes to me yesterday and goes, "What times 3 gives me 16?" So I look at her and I was like, "Count it by 3s." So she goes, she has like, "Oh, it skips it. So there isn't a solution." So she hasn't done much for the fractions, but so she realized that there wasn't a solution to it. So it was super cute. So again, it depends on what structure you're in. It was super cute yesterday. I was so happy. And then I got to go watch them play basketball, and she won the knockout thing they were doing at the basketball. Because she's enormous. Yeah. Well, it's hilarious. So my one niece, she is, here on me, right? Because she's like 5'2". She's enormous. My other niece, who's actually 4 months older, is like that tall. Yeah. But she's getting a grade ahead. So she's with the bigger kids trying to shoot in the bigger basket and having trouble getting it up in the basket. My other niece is with the younger kids, and of course they lowered the basket for them. So she's like, almost level with the basket. Because Dr. Stickles was like, I want to see her go up there and just dunk it because of how low the basket was.
Yeah, and then by knockout, she just jumps up and dunks it.
In your face. That'd be hilarious. In any event, so just going back, I thought that was a good example of the ideas that we're thinking about. It's nice to be able to divide, but that's not a requirement depending on the structure. But the addition, being able to subtract, is a requirement. Okay, so that's where some of these ideas are coming from. So these operations need to satisfy the following properties, and they're going to look a lot like the vector space axioms that we had in linear. Okay. In fact, the vector space axioms we have in linear are talking about having a ring and then also talking about having scalars to be able to multiply by, and those objects, when you abstract that, are actually referred to as modules in algebra. So the vector spaces are a very specific case of that. We're not going to talk about module theory in here. But if you want to take a second semester with me next semester with abstract algebra, we can absolutely talk about it. I see you're all chomping at the bit.
There's a second semester of this?
Yeah. Yeah, we can absolutely do an independent study. I'd absolutely do that. I've done a second semester of abstract several times in the past. I like it, so
We'll see where we are at the end of this. That's exactly.
if you're interested, I'm happy to do it. And my requirements for independent studies are, as long as you're working, you're going to get an A. So it doesn't really matter what the grades are for what I collect and grade. As long as you're doing the work and giving an honest effort, you're going to get an A. And I wouldn't agree with to do the independent study if I didn't think you were going to do the work. So you're going to get an A. It's just a matter of working on it.
Isn't advanced calc probably going to be an independent study?
Yeah, at least right now. Well, the three of you have to have it. So Dr. Olson's going to do it. She'll probably meet with you regularly.
It's us and then somebody in
Is it Ben?
industry. Yeah, I think it is. I don't remember his name. I'm so terrible with names. I know he's also doing a math major, so he also has to take it.
Yeah.
Physics, math, double major. I think he might be a sophomore right now.
Yeah, maybe. I don't know. If there's enough people to do it, we'll do it as a regular class, probably. So recruit some students to take advanced calc.
Come on, guys.
Well, Jenna has to.
Yeah, I have.
Come on, Miss Simon.
No, we don't have other things to do.
We're done after this.
Yeah.
This is our last math class.
What?
Then it's just all teaching.
Well, you still have your math internship and your math
Yeah.
methods, yeah.
Try to convince the music students to come take it.
I have much left.
Go to remind them of.
Yeah. And then you should do some independent studies.
Well, I'm in my senior.
In your senior project, yeah.
It's just like dance. If I had bad calc, they really meant just calc too. Like you're gonna be fine. You're gonna be fine. It's like calc 1.5.
Well,
You'll be good.
Advanced calc is kind of nice because what you do is you basically go back, you know, all the stuff that you skipped over and didn't prove in Calc 1, you prove it.
Oh.
So like intermediate value theorem, you go back and you prove it. What's that? No. Help's like, no, screw that, I'm not doing that.
I feel like that's probably going to be one of the easier groups, right?
Intermediate value theorem? Yeah, I mean, yeah, it's not bad. I like to do intermediate value theorem. It's kind of fun.
Because you just got to prove that it's between it.
I'll stick with my PE classes as my extra.
That something exists between it.
It's basically a consequence of the theorem that says that a continuous image of a compact set is compact.
Yeah,
There's some words in there. Yeah, but you'll do things with sequences. You know, a lot of the things with the sequence stuff. Talking about, I'm off topic. It's fine. We're talking about math. It's okay. So some of the things that you can talk. I don't know what Dr. Olson will do. I know some of the things that I would talk about. You go back and do some differentiation stuff back with definitions. You do some integration stuff with definitions. But one of the things you might talk about are sequences of functions. So, like if you have y equals x, that's continuous, right? If I do y equals x squared, that's continuous. If I do y equals x cubed, that's continuous. But notice that from 0 to 1, this thing gets flatter and flatter and then shoots up. If you do the limit of that sequence of functions, even though each one is continuous, as a function, so I'm not talking about doing x to the n as an object, but as a function on 0, 1, you get the function of 0 up until 1, and then it jumps. So you do a limit of continuous functions and it's not continuous anymore. A sequence of continuous functions and it's not continuous anymore.
Have we ever done limits of sequences? Have we done that?
Not of functions. You've done limits of sequences in Calc 2 and 3 probably. Because you do it when you do like the series tests. You do
Oh,
limits of
yeah,
sequences.
yeah.
So that's another topic that you talk about in advanced calc. One of the reasons why you need this kind of an idea is that we talk about a numerical. You talk about wanting to approximate things with other types of functions. You want those approximations to get better and better, but something is happening here. So you need to make sure the continuity restriction isn't quite enough. You have to do a little bit more and call it uniformly continuous to make sure that the limit actually turns out to be continuous as well. So that's, I don't know if Dr. Olson's going to talk about that particular type of topic, but it ties back to approximation stuff as well. So one of the reasons why you study it. Like I said, I don't know what Dr. Olson. I know Dr. Olson's going to do the class, whether it's 3 or enough for a whole class to meet, but she's definitely doing the class. And like I said, there's all sorts of different things you can do. The way I usually do it is I go back to Calc 1 and start saying, okay, well, let's prove the things we didn't prove before. So like intermediate value theorem. Also, remember when you have a function that's continuous on a closed interval, that you have to have an absolute max and absolute min. That's another concept that you go back and prove. It's called the extreme value theorem. Those kind of things. You might go back and play around with mean value theorem stuff more. Yeah, there's all sorts. It's all sorts of good stuff in there. It's fun stuff. But like I said, I don't remember what Dr. Olson decides to do, but lots of stuff you can do.
Lovely little fundamental law of calculus somewhere in there.
Yeah. All right.
The words,
yes. All right. So let's go back and get these axioms written down since I didn't actually do that yet. All right. So just like in linear, there's a lot of axioms, but like I said, they're going to look like the ones we did in linear. So if we start with 2 elements in R and then operate them together, we have to get back in R again. Actually, I referred to this already as a binary operation. The word, when I say something is a binary operation, I already mean that it's well defined. I already mean that the answer should have been in there anyway. So by binary operation, when I talk about a binary operation, binary means that my inputs are 2 inputs that go in, right? So when you add things together, it has to be 2 things you add together. And then the function has to go back into the set again. So that if we were doing our function notation, that's a binary operation. We mean we have a function on ordered pairs where the 2 different components of the ordered pair come from the set, and then the answer has to go back into the set. The output has to go back into the set. That's the definition of a binary operation. So anyway, this again is referred to as closure. But as soon as I say the words binary operation, I mean closure. Me talking and them talking at the same time. Yeah, I see that Professor Archime's in her office too, so try to keep my loud self from hearing down the hallway. That's why I shut my classroom door all the time, because my voice carries down the hall. All right, so closure makes sense, right? And if I want to have a well-defined operation, I need to make sure that the answer is back where I started. We've talked about that before. What property is that one called? Yep.
I always get that wrong.
Me too, that's why I didn't speak. It's like, oh my god, it's the wrong one.
Remember the regrouping part is important because if you're trying to solve an equation, if you want to add something to both sides, it really gets added to maybe a sum that's already there. I need to be able to regroup so I can do that canceling that you want to do, right? So that's why we need the associativity. What's that one called? Commutativity, yes. No, the commutativity one is probably one you should remember when your professor is a commutative ring theorist.
No pressure though.
So no pressure at all. I do always make the joke about it's not commutative. You're not a hippie. You don't live in a commune. And it's not communicative. It's not a disease. Commutative, yes.
I didn't know it was commutative until like my senior year of high school. I always thought it was commutative.
Commutative, yeah.
Is that what it
Yeah. It's like you go back and forth to work. You commute.
See, I always used commune, like commune, to imagine it because it's fine either way because it's all together. You're sharing the order.
Yeah, they're all by. It doesn't matter.
They took it into their hands. The people are controlling which way they're going.
That's amazing. That's amazing. I love it. Oh, goodness.
Communist numbers.
Communist numbers. Oh, goodness. That's what just says there is something that's the additive identity. If you were talking about two different rings in the same scenario, you might put a subscript on the zero to make sure you're talking about the zero in one ring versus the zero in the other ring. When that becomes more important, again, if you're talking about context, you're talking about more than one ring. But the idea behind that is it doesn't have to be the number zero. That's the additive identity, right? If we have ordered pairs and I want to add them to another ordered pair, the zero element is probably not just going to be the number zero because my elements are ordered pairs. Like when you add vectors, right? When you add vectors in Calc 3 or in a physics class, you add them component-wise, right? The zero in that particular structure is whatever the vector is that has all the zero components in it. Right? That's not the number zero. You're talking about a specific vector, right? So again, we use zero to denote it, but it may not look like zero, and you're used to that, even though you may not think you're used to that. If you've done anything with vectors, you're used to that. It doesn't look like the number zero. All right, so that just says that we have an additive identity. 5 says that for each A and R, there exists, I actually wrote out a B in R such that A plus B equals 0. The way they wrote it in the book is that the equation A plus X equals 0 has a solution. That's our additive inverse. Identity. We've got a few more, but just to mention, and I've mentioned this before, we're going to abstract a little bit more. So we're doing abstract algebra. We're going to abstract a little bit more going forward in the semester. Okay. At this point, we've actually created a specific type of structure that has one binary operation. Okay. The binary. This is just saying we have a binary operation. When you do 2, 3, and 5, those three axioms together, you get what's called a group. I mentioned this the other day, but that's what we call a group. When you add, try that again, 2, 4, and 5, you get a group. When you add in 3, you get a commutative group, and the special name for commutative group is an abelian group, named for Niels Abel, Norwegian mathematician, if I remember correctly. So these are 2, 4, and 5 are the group axioms. 3 adds the abelian group axiom. So in particular, for a ring, your addition has to behave exactly like you would expect addition to behave ever since you were in grade school. Is basically what that says for any ring. Okay, that's all that says. Okay, so it's not changing anything. The last axioms that we have 3 more. Sorry. We have 3 more axioms for a ring. The 6th one says that A times B is back in R again. This is closure under multiplication. 7 says your multiplication is commutative, or not commutative, I just said the wrong word, associative. And then 8 is the my operations play nice with each other axiom. Multiplication distributes over addition both ways. Okay. That's the last axiom that we have for rings. The only thing we require of the multiplication by itself is the fact that it's associative. We don't require anything else for the multiplication by itself. Now, like I said, we also require that it plays nice with addition. Okay, but just as the only property of multiplication that you have that we require is associativity. Okay, that's it. Yeah. When you have a structure with one operation and it satisfies the associative axiom for that operation, we refer to that kind of a structure as a semigroup. It satisfies one of the group operations, so we call it a semigroup, which would imply that there were only 2, but that's just the word it has. All right, semi usually is half, right? Okay. So anyway, when you get associativity and an identity for the one operation, we refer to that as a monoid, and then past that you get group. So the only reason why I'm mentioning it is that sometimes you will hear about the multiplicative semigroup of a ring. That they're just talking about the ring elements specifically under multiplication. The only reason why I mentioned that. Okay. So semigroup just means that, hey, my operation's associative. Okay. Just another way to say it. All right. So those are the ring axioms. So if you want to verify something is a ring, you have to verify that those axioms are met. Now there might be other axioms that or other properties you would like your ring to have, but those require some extra things that aren't necessary for it to be a ring. So again, ring just requires binary operation. Addition's great, right? Addition is exactly like you expect addition to work like you did in grade school. Okay, so that doesn't change. But your multiplication just needs to be associative, right? I don't need to be able to flip it around, and I don't necessarily need to make it have a multiplicative identity. Okay. So if your multiplication is commutative, then we refer to it as a commutative ring. And if there's a multiplicative identity, then we say that we have a ring with identity. Okay. So just to write that down, if your multiplication is commutative, then you have a commutative ring. If there is a multiplicative identity, then you have a ring with identity. Oops. Or sometimes you call it a ring with unity. Remember, we referred to the elements that had inverses as units. That's where the unit he comes from. All of these axioms and these last two definitions are independent of each other. What we mean is that you can find structures in which all of the things are true except for one of them. That's what independent axioms means. That you can, an axiom is independent from the rest of them if you can find a structure in which all of the previous axioms are satisfied, but not the last one. Okay. So to give you an example, if you took the set of even integers, just all the evens, if I add two evens together, I get an even. The additive inverse of an even is an even. 0 is even, so I have an additive identity. Multiply two evens together, I get an even. So even integers satisfy the ring axioms. It's also commutative, right? So the even integers would be a commutative ring, but it doesn't have an identity because there is no multiplicative identity in that case for even integers. So that shows that having an identity is independent of those rest of those properties. That's what I mean by the independent piece. To show that commutativity would be independent of the rest, can you think of a structure that's not commutative under multiplication?
Vector multiplication, or when we did, what is it called? It was abstract vector space where.
I think you're thinking too hard. You can go before vector spaces.
Oh.
What objects did we multiply together and the order mattered? We did it in linear. There we go. Matrix multiplication is not commutative.
Oh,
Yeah. That's why I said you were going too far with the added vector spaces. Matrices satisfy all of those axioms, plus matrices have an identity. So matrix rings make it square, so you can do your multiplication both ways. Okay? So square matrices have an identity, right? Because we know what the identity matrix looks like. Satisfies all those other properties. We did all those proofs in linear as well, right? To show that it really did distribute. However, it doesn't satisfy the commutative property. So that shows that commutativity is also independent of the rest of those axioms. Okay. Generally speaking, from a logic standpoint, that's what it means for axioms to be independent. You can find a structure that satisfies all but one of them, no matter which one you pick. So what that would mean is that I can find a structure that's the addition's not associative, but everything else is satisfied, for example. There are actually things called non-associative rings, which makes no sense to me, but that doesn't, it literally makes zero sense in my brain for what that means, but you can find structures that do those kind of things. Okay. We're not going to spend a lot of time on that. If you want to take a logic class, you can do that too. Talk to Dr. Ruff about that. Oh, there's all sorts of fun things you can do. Oh my goodness, there's lots of fun things in math. I think they're fun. All right. So what the rest of this section is dedicated to is basically create a bunch of examples. Well, most of the examples they have in here are ones that you're already familiar with. So what you're more interested in is what types of rings are there. So we said the first example that I mentioned was the set of even integers. Now remember, we use a z typically to represent the integers. It comes from the German Zahlen. That's why they use a z. For the even integers, we use like 2z. So basically you take every integer and multiply it by 2. This is a commutative ring without identity. I'm not underlining it just for emphasis. You don't really have to underline it. It's a ring, but it also satisfies commutativity, but it does not have an identity. It's funny. All right. To introduce another notation we might see, remember we use the capital M to denote sets of matrices, and then we use the subscript to talk about the number of rows and columns. Right now I put two N's in there. That's redundant when we're going to do square matrices. So a lot of times instead of putting the two N's in there, you'll just put in one N instead. And so you'll know that it's square. Okay. So the M is matrices. The N says it's N by N. The inside here where I put the parentheses, it says, what type of objects are you going to put in for the entries? So these are square matrices with integer coefficients or integer entries. Okay. This is a non-commutative ring with identity. Do you think you could come up with a concept that would give you an example of a non-commutative ring without identity? You have an example of a ring without identity and a ring that's not commutative. Do you think you could come up with a concept that would create the both at the same time?
Yes.
Okay. Would you like to give me an example?
No.
Make the matrix n by k, where k is something other than n.
That won't be a ring because my operation isn't defined both ways. Because my multiplication has to be defined both directions.
Mm.
And in particular, I don't think it'll be defined at all because n by k won't multiply by n by k. I have to have square to make sure that my operation is defined.
Oh, what about the identity matrix question?
So I want to create something without an identity. Yeah, so I'm trying to find a non-commutative ring. So if I'm thinking of a prototypical example of a non-commutative ring, yeah, go ahead.
Did you do the matrix m by n or n by n 2z?
Yeah, that's what I was thinking. I've just put the two together.
Side question:
Yes.
does there exist some shorthand for like a set of entirely variables?
What do you mean?
I mean, I was just thinking like there's the notation z for all integers, but is there a similar notation to denote like purely alphanumeric variables? Say you don't.
Oh, you're saying, is there a way to describe everything not easily? I think. Have you had theory of computing? No. Okay, then never mind. There are objects in which you can define your structure as words, and then you talk about the letters of the words, but you still have to define what the letters are. So a lot of things you can talk about. I have two symbols, A and B, and maybe I don't have any way to talk about exactly how I combine them. I just concatenate them. And so that's my operation, is concatenation. And then you can start talking about, well, maybe they behave nicely with each other and talk about how to shorten that concatenation. But it's more complicated that way. But there's not any particular symbol. What I'm thinking of are typically referred to as what we call free groups. That you've just got a set of symbols and putting them together is literally just writing one after the other. I think that kind of goes to what you were saying, Dave.
Yeah.
But it gets harder to describe what it has to be at that point. And we're not going to do that.
math symbol for the alphabet?
Is there a math symbol for the alphabet? No, you actually typically have to define what the alphabet is. At least not that I know. All right, so this just like I said, we're just getting a few examples of different types of things. We've already seen that all of our Z mod n's are rings. They're all finite. So some of the things we've been writing down are infinite rings. But those Z mod n's and geomatrices, polynomials, Cartesian products, ordered pairs, ordered triples, those kind of things are kind of your go-to examples. Okay. Some of them have certain properties, some of them don't have certain properties. We've already seen in the Z mod n that sometimes you multiply two things together to get 0, and they're not both they're both non-zero. And sometimes if you multiply two things together and get 0, one of them has to be 0, right? So one more definition. A ring with identity, let's have an identity, is called an integral domain, or sometimes we'll just not say the word integral and just say domain, is an integral domain if whenever AB is equal to 0, we have A is 0 or B is 0 for all A and B in the ring. Integral domains satisfy the zero factor property. The reason why we call them integral domains is because they make us think of the integers. Another example, you've already talked about another example besides the integers, which is an integral domain back in Algebra 1 class when you solved polynomial equations, right? How do you solve polynomial equations? Set it equal to 0, factor, set each factor equal to 0. That's using the property that that polynomial ring is an integral domain. Okay. Now, it's kind of a nice example of an integral domain because we don't get inverses in polynomials, right? That's why you talk about all the rational function ideas, right? Because you don't necessarily get an inverse of a polynomial isn't necessarily a polynomial, right? The inverse of x would be 1 over x. That's not a polynomial anymore. Okay, so it really is another nice example of an integral domain. If you can divide by every single non-zero element, it's called a field. Oh, commutative, sorry. So we'll talk about those next time since I'm at 12:15 anyway.